we are going to move on and start using calculus when in kinematics, using calculus in kinematics. There's a plane called a Stratolaunch. I guess it's a rocket launch system involving this absolutely ridiculously enormous airplane. Look at that. Look at the windows on this thing. This is a huge airplane. They plan on strapping rockets in between these two connected fuselages and launching rockets from between these planes together. That's crazy right there, but I love it. Last semester, a representative from Stratolaunch actually came to the university and gave a very interesting talk about this system. So, Stratolaunch uses a plane like the one shown to lift a horizontally integrated rocket to high altitude. That means that you strap the rocket in between them in a horizontal position and then launch it forward, and then it shoots up into space. This saves fuel, something like that. According to the speaker, it actually allows them to set exactly when they want to launch something. They're not as beholden to launch windows as a non-moving launch platform would be. If you're launching something from Kennedy Space Center, then you have to launch at very particular times, very particular launch windows for it to work. But with a system like this, you have much more flexibility in your launch windows because you can just send the plane somewhere else in some other direction to get things started. Well, an example problem for this: at the moment of launch, the rocket accelerates at an acceleration as a function of time. That's how you read this. Acceleration as a function of time is equal to 2 plus 0.6 t squared. And assume that this ends up being in meters per second squared. The initial velocity of the rocket on the plane is 150 meters per second. So the moment of its launch, the velocity of the rocket is 150 meters per second. Find the velocity as a function of time. Find a function that describes the velocity and how the velocity changes with time. And then find the position when the velocity is, I just made up a number, 343 meters per second. We have our acceleration function, 2 plus 0.6 t squared. We know that if we take the integral of this, then we should get the velocity. And I know that a lot of you have not done physics, calculus 2 yet, where you would be taking these integrals, but you can kind of think of it as an antiderivative. Well, it is an antiderivative. And you'd be able to take the derivative of this. That's not too bad. You know, derivative, that 2 would go away. That 2 would get multiplied by the 0.6. It'd become 1.2 times t. Well, an antiderivative is just, okay, what function can we write down to get this as its derivative? That is what an integral really is. And so if we just look at it one term at a time, 2, what function would have a derivative of 2? The function with a derivative of 2 is 2t. This, take the derivative of that and you get 2. Great. Well, what would you have to do to get a function where that is the derivative of the function? Well, what about 0.2 times t cubed? That cubed there, well, that would get converted into a squared, and the 3 would come down and go 3 times 0.2. Well, that's 0.6, and that's 2. Oh, so that must be our integral of the acceleration. There's one thing that we're missing, and you might only notice it if you have already taken calculus 2. There's always the possibility that there's an extra constant on the end of it. Now, if that's just a constant, the derivative of that constant would be 0. And that's consistent with what we see up here. You take the derivative of this with that being a numerical constant, you would still get that. So there's always a possibility that we've left that off. So let's include that and see what happens. Well, I ask you to find the function of velocity as a function of time. That's most of it right there. But I do give you one more hint. I say that the velocity at time is equal to 0 is 150 meters per second. Therefore, I can say 150 is equal to, I'm going to replace all the t's with a 0. So I'm saying that v is equal to 150 when t is equal to 0. So plug in 0 there. Okay, well, that goes to 0. Plug in 0 there. Okay, well, that goes to 0. So I guess 150 is equal to c. Therefore, the velocity as a function of time is, I'm going to put this in the more traditional order, 0.2 t cubed plus 2t plus 150, all in meters per second. We just found the velocity function, just given this acceleration function and the initial conditions, what it is at t is equal to 0. And we got it. Great, that's some calculus right there. Great. The next part was finding, oh, let's see, it was finding the x position, oh dear, my handwriting. We need to find the x position when the velocity is equal to 343 meters per second. That's not too bad, because we've got the velocity right there. Can we use this to figure out a time at which that would be the case? Yeah, probably. In fact, a lot of you have a calculator that can just do this automatically. My calculator, a TI-89, that, as I said last time, is older than most of you because it's from mid-1999, you go to the F2, you go to solve, and you say, well, I want v of t to be 343. 343 is equal to 0.2 t cubed, 0.2 times t cubed, plus 2t plus 150. And then if you hit comma, and the thing that you want to solve for, we want to solve for t. So I hit comma t, and then I close my parentheses. The comma t says solve for t. You hit enter, and you wait a little bit, and then finally it says t is equal to 9.545, I guess, rounding a little bit. So we can just write that here. The time when this is the case is 9.545 seconds. Well, that's not bad. But that's not what we're looking for also. We're looking for the x position when that's the case. To find the x position, we need to find x as a function of time. And to find x as a function of time, we need to take the integral of velocity as a function of time, and the velocity as a function of time was 0.2 t cubed plus 2t plus 150. Doing the same kind of thing that we did last time, we can see that, okay, what's the integral of that going to be? Well, we need to find something whose derivative would be that. And through a little bit of algebra, you can probably tell that if you have 0.05 t to the fourth, let's see, so that 4, if you take the derivative of this, and that 4 would come down, you'd have 0.05 times 4, that'd be 0.2, check, and that 4 would become a 3, check, okay. Plus, okay, what would have a derivative of 2t? Oh, well, t squared would have a derivative of 2t, and 150 t would have a derivative of 150. We can also say plus c at the end of that. But the question is, what is the x position when that's the case? Now, I have no information about what the initial position is in x. What is the initial position when the rocket is fired? I have no idea. So I can't really tell you an exact position. I can just tell you a position if you set the initial position to be 0. If you assume that you're setting your origin point at the moment that the rocket is launched, then the rocket is launched at a position of 0. And so the c would be a 0. You'd plug in 0, 0, 0 for t. You'd say that the initial position is 0, and you'd find that c also has to be equal to 0. Oh, I got a question from Spencer. How can you solve for t without a calculator? Ooh, yeah. You have this equation, and you want to solve it for t. This is not a quadratic equation. You can't use the quadratic formula on this polynomial. Therefore, it would take potentially a lot more effort to do that. If you plug in 343 there, then I'm not exactly sure. Oh yeah, there are algebraic ways of doing this. There are incredibly painful algebraic ways of solving this if you don't have a calculator. I strongly recommend that you get a calculator that can solve that kind of thing. Why was C canceled? I don't really give you an initial position. So let's just assume, let me write this down. Let's assume that at t equals 0, when our timer begins, we're going to start our timer. Imagine having a stopwatch. Start your timer the moment that the rocket launches. We're going to say that at t equals 0, x was equal to 0. So that's saying that we're defining our origin to be 0. We're defining our origin to be the moment that the rocket has launched. Therefore, we can say that at t equals 0, so at t equals 0, x will be 0. So if you plug in 0 for t, then x, which comes out of it, should also be 0. So therefore 0, because that's what x, we're claiming x equals 0, is equal to 0.05 times 0, because 0 to the 4th power is 0, plus 0 squared, which is 0, plus 150 times 0, which is 0, plus c. That all had to equal 0. And therefore c is equal to 0, and therefore we can just kind of cross it out. So all I've done right now is said, let's find the time, and let's find this equation, the x of t equation right there. And this actually, you can also do integrals on calculators like this. Calculators like this are super neat. If I just go to, I have to hit the second button, and then I can hit this 7, which has an integral sign over it. Oh, you can't even see that. There. See that tiny, tiny, tiny little integral sign? I can hit that. I get an integral in there, which is barely visible on your screen. And I can type in 0.2t cubed plus 2t plus 150, and then say comma. I'm integrating with respect to t. So I hit t, and I let it solve it for me, and it gets exactly what we said. I love this kind of calculator. I think that this is that it's worth the $150 to buy a calculator like this. As I said, this calculator I've had since 1999, so it'll last you quite some time if you take care of it. Okay, let's finish this up. We figured out that the velocity is equal to 343 meters per second at that particular time. We can then plug this time in to that equation, replacing all the t's with 9.545 seconds. So just be 0.05 times that to the 4th plus that squared plus 150 times that. And I believe that I have that on the slide. On the slide, it says that the answer is, the slide says that the answer is that x will be equal to 1938 meters. So when you have that velocity, you have that time. And when you have that time, you plug that in and you have this as your position. All you need to do is take the 9.545 seconds and say, okay, we're going to set t equal to 9.545 seconds. I already have this equation expressing my position. Therefore, I can take this time and plug it in for t right there. And so this equation tells me what the position of an object is if I plug in a particular time. If I plugged in 1, then that would tell me the position of the object when t equals 1 second. If I plugged in 10, that would be what is the position of the object when t equals 10 seconds. If I plug in 9.545 in for t in each case, then that'll tell me what the position is at time 9.545 seconds. All right, let's start talking about some more kinematics problems, some more examples. I'd give you several examples in this set of slides that you can work on and that we will work on together right now. You're standing on the edge of the roof of the Crawford building. You lean over the edge just slightly and throw a ball straight up at 15 meters per second. At what time is it 3.5 meters above your hand? At what time is it 3.5 meters below your hand? And tell me one weird thing that happens with this question that has to do with the math or physics of it all. And I give you 4 different equations that you might want to choose from. So I actually, well, this is another one. We can work on this one together as well. It's always a fantastic idea to draw anything that, that you're working on. So here is the drawing of the Crawford building. Great, fantastic drawing from me. There's you on the roof. You throw the ball straight up at 15 meters per second. You're leaning off a little bit, and so let's just pretend that's straight up. Really, it should just go straight up and then straight back down, like along the same path that it took. But that's very difficult to draw and very annoying to draw. So I always give it a little bit of this parabolic action going on. We need to find out when it is 3.5 meters above your hand and when it is 3.5 meters below your hand if you gave it an initial velocity upward of 15 meters per second. And I'm going to tell you that the equation that we should probably be using is this one. Delta x. Well, we're given a few delta x's. This is one problem that you cannot figure out in one equation. You have to have multiple equations to do this because you're asked multiple things. When is it this high up? When is it that high up? Therefore, you have to do certain equations twice. But this is a convenient one. 3.5 meters. Well, delta x can represent when it's 3.5 meters above your hand. That's completely fine. That's equal to initial velocity. Oh, wait, that's 15 meters per second. Here, I have the subscript O, making this V naught, which is the exact same thing as VI, the initial velocity. Remember, that's just a notation that varies from book to book and lecture to lecture and video to video. And I'm talking about the videos that you'll find online, like Khan Academy and whatnot. They will all use different subscripts. And so it's a good thing to start getting used to seeing different subscripts. Anyway, you can plug in 15 for there. We're looking for the time plus 1/2 times A. Can you tell me in chat what A is going to be in this equation? The acceleration is the acceleration due to gravity. So we in this class are going to be using the acceleration due to gravity as 9.8 meters per second squared. I know in different classes in different high schools in different parts of the world, they will actually use different values that are all very close to negative 9.8 meters per second squared, because literally different parts of Earth have slightly different gravitational pulls, very, very slightly different. And so I prefer to use a good approximation that works effectively everywhere on Earth. It'll be less than 1% off, saying 9.8 for that will be less than 1% off anywhere on Earth. So always assume that that's going to be 9.8. But as several people have pointed out, it needs to be negative 9.8 because it's an acceleration directed down. Gravity pulls you down. Gravity does not pull up. Gravity pulls down. Therefore, you need to make that a negative 9.8 times t squared. We can plug all that in, and we get 3.5. We're looking at at what time it's going to be 3.5 meters above your hand. 3.5 is equal to 15, that's your initial velocity, times t, which we're looking for, plus 1/2 times negative 9.8 times t squared. Then you have to use that quadratic formula or use your calculator. And you can figure this out with your calculator a whole lot faster than with the quadratic formula. You can use the math websites that people were talking about, anything like that. But interestingly, you get two answers. You get 0.254 seconds and you get 2.81 seconds. Which one is the right answer? The right answer is actually both. Both of these are correct answers because when you throw the ball up, it passes by this 3.5 meter line twice. Once on its way up, and then it reaches some maximum point, and then it passes by it again. So both of these are correct answers because at both this time and at this time, the ball is 3.5 meters above your hand. You can see it has to pass by that line twice on its way back down. Great. We also need to figure out when it's going to be 3.5 meters below your hand. And so we use the exact same equation. We can plug in negative 3.5 instead of positive 3.5. Everything else stays the same. We are just changing the position that we are looking at. The whole rest of it stays the exact same. The only thing that's changed is we've gone from looking when is it 3.5 meters above to when is it 3.5 meters below. And so therefore we go from the positive 3.5 to answer that question to a negative 3.5 to answer that question. Then we do the quadratic formula again, and we find two answers, 3.28 seconds or negative 0.218 seconds. You can see that I've already crossed that out because it's negative. That would imply that it was 3.5 meters below you before you threw it. That doesn't sound realistic. So in physics, one of the convenient things is physics deals with real world situations. Math, they just deal with numbers, but physics and engineering, oh dear, deal with real life situations. So you can ask yourself, does it make sense that it would be below my hand before I threw it? Probably not. That would imply that it was a time-traveling ball, which is not reasonable. So we can assume instead that it's below my hand 3.28 seconds after I've thrown it. You can then look at all the numbers that you've gotten and say, okay, it first gets to 3.5 meters above my hand 0.254 seconds after I throw it. That makes sense. I throw it and it very quickly gets to 3.5 meters above my hand. And then it takes a little bit of time to go up and then start coming back down and then go through the 3.5 meter line above my hand. And it takes that much time to do that. And then some amount of time after that, it's 3.5 meters below my hand. So the first point, the second point, both at 3.5 meters above my hand. And then the third point, 3.5 meters below my hand. They are in order. Time-wise, they are in order. A spacecraft is landing on the moon. It has a downward velocity of 0.8 meters per second when it is 5 meters above the surface. At what speed does it hit the ground? The acceleration due to gravity on the moon is 1.6 meters per second squared. This is another good kinematics problem. I actually give you all the answers right through here. The equation, I didn't give you the equations that you could use, but if you look through the equations, this one has everything that you need. You're looking for the speed at which it hits the ground. Now, I know a lot of people want to say, oh, the speed that it hits the ground is 0. And I know that it feels like it should be, because when it hits the ground, it stops. But imagine this. Imagine that you punch me in the face like that. Okay, at what speed did your fist hit my face? You might say, oh, my fist stopped when it hit my face, so I hit at 0 velocity. Is that going to hold up in court? Probably not. You have to calculate how fast the impact happened. Like an impact like that versus an impact like this are very different impacts. You can have fast hits or slow hits like that. You don't hit at 0 velocity. You hit at some speed, and it might be fast or it might be very slow. Calculating that speed that you hit is very important. Don't assume that you hit at 0 velocity. Sometimes you will. Sometimes you might hit at 0 velocity. I could take a pen and I could throw it up at the ceiling, and if I've done all my calculations just right, it could just barely touch the ceiling. Say the ceiling's right there. It just barely touches the ceiling before falling back down. That could be a 0 velocity collision. That's really tough to do, and that's really rare in nature. So it will be very rare that we have problems like that. In general, assume that an impact velocity is not going to be 0. When I say something hits something, find the velocity that it hits. You've got to actually do some calculations and not just say it's 0. I've seen this mistake a lot. That's why I wanted to bring that up. Well, I give you this equation. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in position. And then we need to figure out what to plug in there. This is where our notes on what is positive and what is negative come in to be very important. Our initial velocity is down. A spacecraft landing on the moon has a downward velocity of 0.8 meters per second. Therefore, we should give it a negative sign. Now, that's not going to matter at all because we immediately square it up here. This initial velocity gets squared. Therefore, what does it matter if it's positive or negative? It's going to end up being positive in the end, but it's still good to remember to make this stuff negative. The acceleration is also going to be negative 1.6 meters per second squared. So plug in the negative 1.6 meters per second squared there, because gravity pulls down on any planet, or moon in this case. And our change in position, now this is one thing that does bug a lot of people. Our change in position is also a negative amount because we are going down to the moon. If I was coming up on an elevator like buried inside the moon, then I'd have a positive delta x because I'd be coming up. But if I'm going down, I need to remember that my delta x is negative. So all three of these values are actually negative because they all represent something going down. An initial velocity that's down, an acceleration that's down because gravity pulls down, and my spacecraft is going down. Well, I plug in those numbers there, and then the rest is super easy. I get 4.08 meters per second for my V final over there. Just ask your calculator. Note that I got a positive number. Really, I should be saying that this is a negative number because it's hitting the ground, except I do ask what speed does it hit the ground, and speed isn't a vector. Speed is a scalar. Positive and negative doesn't really matter as much. This is one of those cases that we all know what's going on. We know that the spacecraft is landing, and therefore it's going down, and so the velocity that it's going to hit with should be a downward velocity. We know that when we think about it. Our calculator is going to give us a positive number. In this question, it doesn't really matter at all because it's so obvious. However, in a lot of questions, you should be specifying, oh yeah, this is actually negative because it's going down. This semester, that's actually going to be a lot harder because of how the tests go, because they're just going to be mostly multiple choice with a little bit of free response, but the free response is going to be numerical. So really, you don't have to worry about that too much this semester. These kinds of conceptual differences, be prepared to understand that kind of thing in the future and say, oh yeah, when object A hits object B, object A must have been going towards object B at the time. That's just something for when you do this in the future.